on combustion reactions.
Around 1700, a scientist that conducted experiments involving combustion thought the reaction involved the escape of a wild spirit from the burning material.
Something that helped get closer to the reality of the combustion process was the discovery of oxygen by Swedish chemist Carl Wilhelm Scheele in 1771 and by English chemist Joseph Priestley in 1774.
Later, French chemist Antoine Laurent Lavoisier used his discovery to frame a new definition of combustion. Combustion, he speculated, is the process of some material combining with oxygen. Lavoisier conducted many experiments involving very careful weight measurements. His results were so convincing that the new oxidation theory was widely accepted in a relatively short period of time.
More and more research led to new discoveries and details on characteristics of combustion. Despite these discoveries, the actual theory of combustion lacked a clear concept of energy, and therefore there was a lack of knowledge of the critical role that energy plays in combustion.
American-born English chemist Sir Benjamin Thompson's experiments with heat in 1798 revealed evidence for the concept of heat as a movement of particles. Development of a kinetic theory of gases based on the fact that heat results from the motion of molecules and atoms, of thermodynamics and of thermochemistry, all in the 19th century, finally explains the energy aspects of combustion.
Today we have more accurate descriptions of what happen in different reactions. A chemical reaction is any process by which the atoms of one or more substances are arranged to form different substances. Today, a combustion reaction is known as a reaction that occurs when a substance reacts with oxygen, releasing energy in the form of heat and light.
The general form of a combustion reaction is a hydrocarbon plus oxygen reacting to produce a carbon dioxide plus water.
Generally, it releases heat and light since it occurs so quickly, and anytime something burns, usually it's a combustion reaction.
A complete combustion reaction is when there is a sufficient amount of oxygen for the substance to react with. The products of a complete combustion reaction are water and carbon dioxide. This image of a blue flame shows a complete combustion reaction because the light is blue and it emits more heat than light.
An incomplete combustion reaction is when there is not enough oxygen for a complete combustion reaction to occur. The products of an incomplete combustion reaction can include carbon, carbon monoxide, carbon dioxide, and water. The image shows an example of an incomplete combustion reaction, and you can see that it emits more light than it would emit heat.
Some real-world applications would be that humans have been making practical uses of combustion for thousands of years. Cooking food and heating homes have long been two major applications of the combustion reaction. The first engines employed the combustion of some material, usually coal, to produce heat that was used to boil water. The steam that was produced was then able to move pistons, which are sliding valves, and drive machinery. That concept is essentially the same one used today to operate fossil-fueled electrical power plants.
Inventors found ways to steam engines in transportation, especially in railroad engines and steamships. The discovery of a new fuel, gasoline, and a new type of engine, internal combustion engine, led to more modern methods of transportation that are common today. Today, most forms of transportation depend on a combustion of hydrocarbon fuel, a compound of hydrogen and carbon, such as gasoline, kerosene, and diesel oil, to produce the energy that drives pistons and moves vehicles.
Some other real-world implications are smoking, campfires, Bunsen burners, explosives, and fireworks. The list of combustion reactions used in everyday life goes on.
In these two images are one example of natural combustion, which is the hot charcoal, and one example of man-made combustion, which is the jet engine.
Current research focuses on efficiently using fossil fuels and minimizing the impact of pollution emissions from combustion chambers for problems like combustion in diesel engines, gas turbines, and rocket propulsion. Current research activities of the Combustion and Propulsion Group focus on a fundamental combustion property of biofuels for aviation and ground transportation,
Soot and particulate formation in liquid and gaseous fuel flames at elevated pressures representative of gas turbines.
Dynamics and structure of premixed and non-premixed turbulent flames.
Structure of laminar diffusion flames.
Thermal oxidative stability of conventional and alternative aviation fuels.
Laser-induced incandescence technique for soot and particulate diagnostics. These experimental studies are complemented by high-fidelity numerical stimulation in collaboration with CFD and Propulsion Group.
International groups have been collaborating for some of these subject areas.
Some real-world issues include the use of combustion as a power source has had such a dramatic influence on human society that the period after 1750 has sometimes been called the fossil fuel age. The widespread use of combustion for human applications has always caused significant environmental problems.
One example of combustion in the real world is carbon monoxide. Carbon monoxide is a toxic, poisonous, potentially deadly gas that sometimes reaches dangerous concentrations in urban areas and around the world.
Oxides of sulfur and oxides of nitrogen produced at high temperatures can also have harmful effects. A common problem associated with these oxides is smog and acid rain.
Carbon dioxide itself is a huge issue. It is thought to be at the root of recent global climate changes because of the enormous concentrations it has reached in the atmosphere.
A possible future to assist in minimizing pollution from combustion reactions.
Reverse combustion and carbon recycling. It is a reverse combustion reaction that converts the carbon dioxide back into hydrocarbons.
Use an amine-based solvent solution to absorb extra CO2 after a reaction.
The process's source will be a renewable energy source, most likely some sort of a solar-powered source.
Reverse combustion and carbon recycling. The economic feasibility of this process will ultimately depend on the cost of raw hydrocarbon resources balanced against the cost of the capital equipment for the reverse combustion reaction and the potential savings from reduced carbon dioxide emissions.
Private companies such as Liquid Light, as well as national laboratory projects such as Sunshine to Patrol, are trying to make this become a reality on a large scale.
While this does nothing to reduce carbon dioxide that is already in the atmosphere or reduce emissions from downstream burning of fossil fuels, such as transportation, this process can be added to the existing infrastructure of energy-producing plants and significantly reducing the future greenhouse emissions from this major player.
Now we'll talk about some information we found from this textbook. For more information, you can read it because it can easily be found online.
The most promising directions for novel combustion strategies for high efficiency, clean ICEs and GTs involve combustion of lean or dilute fuel-air mixtures beyond limits that have been reached to date. In general, the new combustion strategies require operating near poorly understood limits of combustion stability and/or at conditions for which the combustion reaction zone development in IC engines and stabilization in GTs are not understood. A major additional complication to the challenge is that the fact that these strategies are typically fuel sensitive. This sensitivity adds great uncertainty given the emerging fuel picture and means that a greatly improved understanding of how fuels will impact the various combustion strategies will be required to enable and optimize efficient, clean transportation propulsion systems for the emerging diversified fuel source future.
Fundamentally, new research opportunities occur when the fuel and the combustion strategy can simultaneously be optimized, but the increase in a parameter space will require new conceptual and algorithmic methods for data analysis and automated recognition of large-scale property correlations. Adaptive learning algorithms and automatic optimization tools may provide a means to control real engines based on end product metrics of performance, efficiency, and emissions. The control history of such an engine provides data on a response function connecting a chosen, not necessarily optimal, set of sensor inputs and a set of available control parameters. Predictive modeling and rapid laboratory measurements of a wide range of fuel characteristics and combustion properties is planned. The dimensions of this problem will necessitate high throughput computation and analysis tools. Real engines may not be scalable to sufficiently high throughput applications, and they may not provide sufficient control of chemical environment, fluid mechanics, or physical parameters to determine fundamental principles for the effects of fuel characteristics on combustion. Surrogate systems, an idealized combustion reactor, will be required and must be validated for comparison of real-scale systems. Finally, the interpretation of this wealth of data will likely employ a systems approach of complex and collective phenomena. Crucial knowledge will derive both from a sum over individual physical or chemical details and from decoding macroscopic observations.
The scientific challenges include advances in quantum chemistry methods, new theories for collisional energy transfer, new reaction theories, and experiments to validate or challenge these predictions. Existing quantum chemistry methods quickly must trade off accuracy for molecular or transition state size as the number of atoms increases. Many crucial combustion reactions are known to occur non-diabatically over complex energy surfaces, rearranging by virtue of high non-thermal energy states and mediated by poorly understood collisional energy transfer. Despite a substantial body of experiments of elementary reaction kinetics for relatively small species, few experiments or theoretical studies exist for even modestly large molecules above room temperature, and many of those include reactants without product identification. We must understand the kinetics of reactions that involve multiple sites for radical attack and have numerous competing isomerization and dissociation channels. It will be important to delineate the balance between oxidation and decomposition for large fuel-generated radicals. While paraffinic species have received considerable attention to date, other classes of components with significant content in future transportation fuels have received little or no attention on kinetics, including components such as aromatics, naphthenes, silyl alkanes, and olefins, as well as large polycyclic aromatic and paraffinic molecules and radicals. Such studies are needed over the full range of temperatures.
That concludes our presentation on combustion. Thank you for watching.